So let me start by thanking Angel, Fernando, and Pablo for the idea of organizing this celebration meeting and for organizing it. And I'm really happy to be here, to have the possibility of celebrate Luis' birthday. We have collaborated through several years. I first came to Madrid in '94. Angel was finishing his thesis. I came for 6 months and stayed for 3 years, more or less. And I will overlap with other speakers, but the collaboration with Luis was always very enlightening and enriching, and especially for the ways in which he is able to look at the physics problems, having positive ideas from null results. And also happy to be here because of a friendship that remains along the years beyond physics. And so I'll try to give some ideas about some work I've been doing on double field theory, and motivated by some first work we've done with Luis and with Luis, Ana Maria, and Pablo, and dual fluxes. No, should went there. It's here. So we'll motivate the presence of dual fluxes from T and U duality. This is the work we've done with Luis. And then go to double field theory, give some ideas, and see what the connection of double field theory with a bosonic sector of supergravity is, and how double field theory can provide some geometric interpretation of fluxes. And if I have time, I comment on some extensions in order to include U duality into the game, in some comments. So, of course, if we want to deal with string theory, it's clear that we have to see how to establish a link between a 10-dimensional theory of extended objects, strings, with our observable world. And that means more technical words in terms of 4-dimensional particle models with broken supergravity, and that should include the standard model information. And in order to establish this link, I mean, there have been different approaches from bottom to top. I mean, try to start with a model similar to the standard model, as close as possible to the standard model, and try to embed it into, I mean, local model, try to embed it in a global, well-defined string theory. This is the bottom top approach. Or try to start with a well-defined string theory and find a suitable compactification manifold in order to obtain something close to the standard model, as close as possible to the standard model. Luis worked on both directions. And I have a proof of this in a picture where everybody was trying to download the standard model for the higher dimensions, even using all possible means, and involving the family, friends, and everybody. That was in Boca del Asno, I think, no?
What is it?
Boca del Asno was the name, close to Segovia, some years ago. So one of the problems we find when we look at these models is that many of the fields related to the shape and sizes of the compactification manifold are not well defined. So this is the problem of fixing the moduli. And so here's where the fluxes come into play, and they can help in fixing them. since the string theory has different anti-symmetric forms, for instance, three form associated to the anti-symmetric two form, and there are non-trivial cycles, then we can have non-vanishing fluxes, and whenever we find or we fix a flux, which should be an integer by quantization consistency, then the manifold is not arbitrary, and so somehow the moduli can be fixed. And this manifests as the presence of a superpotential, which depends on the different fluxes. And so, in principle, moduli can be stabilized using fluxes, and then avoid long-range forces, Susy breaking mechanisms appear, and new phenomenology. So for considering flux compactifications, usually one starts with an effective theory in 10 dimensions, effective theory, a low energy limit of a given string theory, then one compactifies in presence of these fluxes, and one obtains a so-called gauged supergravity. Means supergravity with scalar fields charged under non-abelian symmetries. And the quantized fluxes are the gauges in these theories, can be identified with the gauges. So more or less the situations like this start with an effective theory, low energy, a limit of a string theory, type 2A, type 2B, hypnotic, etc. If we were to compactify it onto a torus, then we would obtain a four-dimensional ungauged supergravity with abelian fields. Instead, if we compactify it in the presence of fluxes or on more general objects like twisted tori, what we obtain is four-dimensional gauged supergravity, which as I mentioned, it is a deformation of this ungauged supergravity. So let me say some words about n=4 supergravity. N=4 supergravity has a global group, which is this one here. The gauges can be encoded into representations of this group, and 220. This is the three-form antisymmetric representation of OC6, and can be the gauges can be separated into so-called electric or magnetic fluxes, and there could be also some gauges in the vectorial representation of OC6. And you can write down a scalar superpotential depending on all these gauges, and on some matrices here, which are matrices that encode the content of the scalar fields. There are 36 or plus 1 scalar fields. That will be the moduli in a string compactification. So this is just a brief review. And what one finds is that when we compactify the string or the effective supergravity theory in 10 dimensions to 4 dimensions, one obtains a supergravity theory like the one I've shown before, or an orifol of it, depending on the kind of compactification you perform. But you do not obtain all the possible gauges. For instance, you start with type 2A, you obtain a supergravity theory with some fluxes or some gauges turned on. You, for instance, with type 2A, you start with type 2B supergravity and obtain another type 2B supergravity in 10 dimensions. You obtain another supergravity in gauge supergravity in 4 dimensions with other gauges. And for instance, if a way of seeing that is start with type 2A, compactify to 4 dimensions, you obtain a given superpotential. It's a model for compactification. Start with type 2B, obtain a type 2B superpotential, and both superpotentials are different, and they are not connected by T-duality transformation, which is the symmetry that you would expect to relate type 2A and type 2B on a torus compactification. So it was, in order to enforce this T-duality invariance, it was proposed to, to include new fluxes in objects in the theory in order to, for both superpotentials to match and also to match them with other heterotic, etc. Compactification. So new fluxes must be incorporated. I'm not going to go through the details, but new fluxes, some of them or many of them do not have a clear interpretation in terms of the 10-dimensional theory. And even S-duality can be introduced into the game. So if you do this, enforce T and S-duality, then all 2 times 220 gaugings can be obtained, and there is a perfect match with the gaugings that one obtains in a supergravity, a gauge supergravity theory. So somehow we could say or interpret this as indicating that the gauge supergravity in 4 dimensions contains some information about the stringy aspects of the theory, something that is lost when you start with an effective supergravity theory in 10 dimensions, because things like T-duality are not present in an effective theory. In the windings associated to T-duality are disregarded in an effective theory. So somehow the 4-dimensional gauge supergravity could contain this information. So here comes the double field theory. Double field theory is a kind of name for different attempts to include T-duality into a field theory description. Something which is rather strange because it's kind of blind alley in the sense that it should incorporate something which has to do with extended objects, the possibility of strings for wrapping non-trivial cycles, and this is a theory of particles. In the most simple way, T-duality means exchanging the radius by inverse of the radius, but exchanging windings and momenta, something which is not present in a usual field theory. But the idea, put forward these people here, is that we have this compactified momentum, and we can write a coordinate as dual to this momentum, and we have these windings, and the proposal is to write also a coordinate dual to this winding, and we call it X tilde here. And so try to define a theory in terms of this double space with the original coordinates plus some dual coordinates. And was associated with this momenta and windings here. When this is for a circle, when we are in d dimensions, the symmetry is a bigger one, which is this ODD transformation invariance. So this was the road I've shown before. Start with supergravity, obtain supergravity in 4 dimensions. Now we extend our supergravity theory to a field theory, but depending on the double and twice the coordinates. And then we will try to study the compactification of the double field theory to 4 dimensions, but a geometric compactification, some twisted torus. And well, what I will try to show is that this compactification leads to the bosonic sector of this gauge supergravity. I mean, well, different people have contributed to it. I say the bosonic sector because the starting point is to, double the coordinates and define some starting fields for define the field theory. And in the first proposal, the fields were just the massless modes of the string in 10 dimensions. The metric, the anti-symmetric tensor, and the dilaton. So then it was extended to include vector bosons, massless vector bosons, and some proposal for including fermions and all that. So this is a kind of first proposal. So this is the framework. We start with this G and B field. They can be encoded in an ODD invariant metric H. And then the idea is to write an action in this double space in terms of D fields. And of course, if we throw away the dual coordinates, this action should reduce to 10-dimensional gravity theory. So, which is written here. So somehow, and this action in 10 dimensions, we know it is invariant under the diffeomorphism's usual supergravity in general coordinate transformation. So if we want to write an action in terms of double coordinates, it should have some kind of generalized diffeomorphisms, and these diffeomorphisms should reduce to the usual general relativity objects when we throw away the dual coordinates. Well, an action can be written in terms of this object here, which is defined in terms of second derivative of the metric, and this D term which contains information about the dilaton. As I mentioned, there are general diffeomorphisms that tell us how, for instance, the metric or the dilaton transform. These diffeomorphisms, generalized diffeomorphisms, reduce to the usual ones in the limit of throwing away the dual coordinates. Once you write these diffeomorphisms, you have to check that they close, the algebra diffeomorphism close, and in fact, we can check that they close up to some constraints. So the Jacobi identity closes up to this constraint. And the first proposal, this constraint, a solution to this constraint is the so-called strong constraint, which is something like that. Choose whatever two arbitrary fields, and they must satisfy this condition. So they solve the equation, the consistency equation, but it is easy to check that finally they lead to the condition that the fields all depend only on x or only on x tilde. So even if we started with doubling the coordinates, finally the answer is that you must just have the coordinates in order to have consistency. Well, this was the first proposal, but there are ways out of this. And they come from considering, maybe this is not the most general possibility, but it gives an alternative possibility. Perform a kind of Schwarz compactification of the double field theory. So we start with some space-time coordinates, some internal coordinates, and propose a kind of Schwarz ansatz for compactifying this double field theory, which is the usual one, but in the double number of coordinates. Just write the metric twisted by some matrix here, which depends on the internal coordinates, the usual thing. Also, the gauge parameters of these generalized diffeomorphisms, they are written in terms of space-time will be finally 4 dimensions, times an object dependent on the internal coordinates, and then use the usual techniques of Schwarz compactification. And finally, we will see that the part, well, here's compactified to n dimensions. But this could be taken as 4 and this 6. So we'll see the part of the space-time, the dual coordinates of usual space-time will be thrown away. In fact, they will be thrown away by a consistency constraint. And we will still have a double internal space, dependent on 12 coordinates, let's say. So these were the original objects, and then performed the usual dimensional reductions. I mean, selecting the space-time indices and the internal indices, and you obtain these objects here as usual. And also start with the generalized diffeomorphisms we have at the beginning, and write them in terms of the space-time and internal objects, and you see that we find the correct transformation properties. I mean, in the sense, for instance, this is the transformation property of the gauge vector, which contains the usual gauge transformation with some objects I will describe right now, the usual derivative of the gauge parameter, and this is just the Lie derivative because it contains not only gauge transformation but also space-time transformation. So these are the expected transformations of a four-dimensional theory. And now the closure constraints that we needed in we showed before become some constraints on this gauging here, which are the gaugings here. So these gaugings are functions of the U's, which were matrices depending on the internal coordinates, double coordinates. In fact, they can be written in terms of this, which is called now Bison-Vogt or something like that, connection. And these are just functions of these internal twists. So the gaugings in these formalisms are objects that can be derived from the twist in the Schwarz compactification. And there are, you can show there are 220 gauges. And so an effective action can be written and a scalar potential is obtained. Well, covariant derivative, etc. And then it's easy to see that there is a perfect match between these objects obtained from twists and the electric gaugings in a supergravity theory and the H matrix and the scalar matrix, etc. So we are recovering the sector, the bosonic sector of n equal 4 supergravity by performing a geometric compactification of a theory with a double number of coordinates. Well, I will finally, the closure of all the constraints in this compactification is achieved by considering just these quadratic Jacobi identities, which are the same kind of identities that are found for consistency of n equal 4 supergravity theories. So these are consistency relationships that must be imposed in order to have closure of the algebra. And there is a strong constraint on the space-time part, which is nothing but requiring that the space-time part depends only on half of the coordinates. So you have a strong constraint of the space-time part, but on the internal part, we just have the quadratic constraints of n equal 4 supergravity. So we can avoid the strong constraint in all coordinates. So this is the same I've been saying before. And just, I'm not going to go through all this thing, but let me just mention that we can somehow go from double field theory to something we call extended field theory in order that includes not only T-duality, but also S-duality. This is the idea. So consider a kind of geometric compactification of something which has a an internal torus of 56 dimensions, which is the dimension of the vectorial representation of E77, which is the global group of n equal 8 supergravity associated to U duality. So the proposal is to start with a theory with an internal sector that now, instead of having double the coordinates, instead of having 12 coordinates instead of 6, we will have 56. Well, then there will be generalized diffeomorphisms, and they must keep the structure of E77 U duality group, etc. And all things are not finished, but the internal sector then perform a Scherk-Schwarz compactification. And we have looked at the internal sector only, and I think the nice thing is that we can do a kind of geometry, in the sense we can define internal covariant derivatives. The commutator of covariant derivatives gives a Ricci tensor. We can have a scalar of the constructed out of this Ricci tensor, and we can have this scalar object, and it coincides with the scalar superpotential. I mean, performing the correct identifications. It coincides with the scalar potential of n equal 8 supergravity. With again the fluxes here, the gaugings here can be interpreted as objects coming from the twists in the Scherk-Schwarz compactifications. They are 912. They satisfy all the respective relationships that appear in the n equal 8 supergravity. So this just to conclude. So the idea of DFT, I mean the double field theory, is to include some string information into a field theory, defines objects on double space. There are some constraints that must be satisfied, and they coincide in a kind of Scherk-Schwarz compactification with usual constraints that are required in n equal 4 supergravity. And all the gaugings that appear in an n equal 4 supergravity now can be given a geometric interpretation in terms of this strength theory in a double space. Well, there are different things to look at. Well, there have been some work on including the Ramon sector. Well, the E77 thing already contains the Ramon sector, contains all the bosonic sector. How to include branes? I mean, it could be some kind of exchange branes related, but all possible T dualities and S dualities, etc. And the full consistency, I mean, relationships between the double field theory and string theory is still to be clarified, I would say. Well, different, I don't know what is that? Different contributions, and let me finish with this picture, and I think it's Peñalara, also some years ago. Here you see Luis, Carmen, Tony is here. Carmen, Marta. So, thanks a lot, and feliz cumple.
Thank you. Questions? Peter?
You said that you relax the strong constraint. Do you also have to relax the weak constraint in order to...
Yes, I mean, you relax, replace them by another constraint which appears to be this quadratic constraint on the internal space.
But the weak constraint, as I understand, is quite important in string theory because it reflects level matching. So I'm not sure whether we, or at least I do not understand how you can really relax it in order to get all possible gaugings in the four-dimensional theory. This is still what I do not completely understand here.
Well, from the point of view of double field theory, you can obtain a consistent double field theory in the sense that you find generalized diffeomorphism, the algebra of them closes and imposing that.
Correspond to string compactification if you relax these constraints.
It's not completely clear if they. I mean, even if you impose the strong constraint, I would say that the connection is not still clear in the sense that you just choose to work with only the 10-dimensional massless modes and other things. But it's for the point of view of double field theory, it is perfectly consistent. Yes,
so, how many supersymmetries do you have in the double space before?
Zero. I mean, no. I mean, this is just a first step, so we are not considering fermions here. So the fields are just B mu nu G. So there are no fermions here, so there is no supersymmetry. So I mean, it's yes. I say, well, we are obtaining the bosonic sector of n equal 4, but here there is no supersymmetry at all.
If you would continue playing this game by compactifying more dimensions and having larger symmetry groups, do you think that you could connect with these E10 or E11 formulations of string theory? Because they are used to classify fluxes, and I think that there would be some analogies.
Yes. Well, this is something we are fighting with. Because try to understand E10 or 11. I mean, in fact, when you do the double field theory, you can start with a O1010, let's say. I think that you are working with all compactified theory coordinates, and then somehow decompactify some of them, and you obtain a 4-dimensional theory with an internal phase, etc. Now we want to do the same thing, but including U duality. You would have to find a group containing E77, and in some decompactification limit, it should lead us to space-time times E77. So this group could be E10 or 11. And I mean, we know that there are connections. We are working with it, trying to understand them. But yeah, there should be a connection. There should. You can classify fluxes using them.
I think I may have already asked you this before, but I forgot the answer. Do you have, by doing this, any way to find a way to write an action for a self-dual field strength? Like for
an action?
For a self-dual field strength. Because that's usually a problem that you don't have a covariant action when you have self-dual.
I don't know if I understand.
Like the F mini rho sigma of type 2b, it is self-dual. So you cannot write an effective action for it.
I know.
No? Okay. And then I have another point. You have 56 dimensions in the 7 case, plus the 4 extra for our 4 dimensions.
Yes.
So that's up to 60, which is very good.
Yes, that's the reason we are working on
Next year will be hard.
Have to go to 11 or 7. 11.
Okay. Questions, comments? Thank you again.